Good evening. We'll start with hidden Markov model for part of speech tagging. Part of speech tagging helps us to identify whether the words in English text is a determiner, verb, preposition, noun, adjective, and so on and so forth. Now the question is, how are we going to identify the word which follows another word is a noun or a verb, and in what probability can they occur? And for which we are supposed to identify the instances. Certain cases, the assumptions are taken in such a way that the successive instances are independent, but in reality, the successive instances are dependent. And therefore, Markov model helps us in modeling the dependencies. It tags along and then it tries to predict the future uh, where the previous or the past doesn't matter, but it tries to identify the future or predict the future based on the current input. We have a concept termed as discrete Markov model, where the states or system is defined into different states, which we take it as S1 to Sn. At a particular point of time, t, you have a state, the system is in state qt, which is equal to si, which is one among the states which are defined. Now, if you really look into it, the system will be in sj at the time t plus 1, provided the system is there in state si at time t. And the system should have been in sk at time t minus 1, and so forth, so on and so forth. Now, based on the study, it has been equalized to the system will be in state sj at time t plus 1, provided the system is there in state si at time t. There is also something called as transitional probability. What is transitional probability? The system moves from state 1 to state uh, 2 from time t to time t plus 1 with a probability of 0.01, 0.02, 0.001, and so on and so forth. So we have a matrix where it is an n cross n matrix, which talks about the dependency of one state to itself and from one state to the other, where n is the number of states. To start with, the system works with an initial probability which has been considered as qi. And the observed probability will be equal to q, which we have to calculate based on the transition probability as well as the initial probability. Now here you have a Markov model with three states. And we'll just take an example of state 1, which has an initial probability of pi 1. Now, since we have three states, the next state would be either the system can stay in state 1. Now, if that's the case, what's the probability? A11 is the probability. The system can move on to state 2 with state 12 as the probability. The system can move on to state 3 from state 1 with A13 as the probability. The sum of A11, A12, and A13 will be equivalent to 1. Now, here's an example where you have three baskets, each full of balls of one color. S1 has red, S2 is blue, and S3 is green. Therefore, you have an initial probability saying 0.5 of red, 0.2 of blue, and 0.3 of green. And now, this is the first basket, second basket, and the third basket. The occurrence of S1 to itself is 0.4. S1, then if I could draw the red ball first, followed by the blue ball next, then the probability is 0.3. If I could draw the red ball first and the green ball next, the probability is 0.3. So the observed sequence is S11, S1, S1, S3, and S3. So how do I define it? I try to take the initial probability for the first state. Initial probability is P of S1. The second state, P of S1 based on the previous state S1. The third one, S3, P of S3 based on the previous state S1. The last S3 is P of S3 based on the previous state S3. And if you could multiply it, they have defined it as pi 1. Pi 1 is 0.5, A11 is zero point 0.4, A13, 1 on 3 is 0.3, and A33 is 0.8. So you have an overall probability of 0.048 for the defined sequence. Here you have another example where you have sunny, rainy, and snowy days, which are three states of the system. And this slide shows the next state. Sunny sunny to sunny is 80%. The probability of sunny to rainy is 15. Sunny to snowy is 5. Similarly, rainy to rainy is 60. Rainy to sunny is 38. And rainy to snowy is 2%. Similarly, same goes in for snowy. So this transition is represented as A, whereas the initial probability is 0.7, 0.25, and 0.05. Now to identify this, the probability of this sequence, where the first one is sunny, second one is rainy based on sunny, third is rainy based on rainy, the next one is rainy based on rainy, snowy based on rainy, and snowy on snowy. Based on the given input, this is the probability what we take into account. So the components of the Markov chain are, we need, there are different, for example, there are different states in the system, and each state has an initial probability, each state has a transition probability. So the components of the system are Q, which is the set of states, the transition probability, and the initial probability. Now we also have something called as a hidden Markov model. Now what does this do? This takes in the assumption. The two assumptions are, the first one is Markov assumption, where the probability of Qi is based on Q1 to Qn minus 1, I minus 1, which is considered or shortened as P of Qi based on the previous state it is in, which is Qi minus 1 alone. Now the output dependence, uh, it has to take from Q1 till Qi, but we'll confine it to the current state of the system, which is Qi. And therefore, we'll add the components of the hidden Markov model, which is Q, A, the transition probability, and based on the observations so far, it is based, you have O, the observation likelihoods or the emission probability is B of O of I, which we'll see what it is, and then the initial probability is pi. Now, with this example, let us try to work on with the vertebrae decoding, but then we talk about the specific instance. So what happens? The transition probability is moving from one state to other. Emission probability is based on T4, what word occurs. Okay, so you have to look up onto the emission distribution. So what does it do? It represents the probability with a word every time. Okay, so these two are main things. Now here is an example where AB matrices are defined. A sample, but we directly look into an example where you use vertebrae algorithm for decoding. So how do I do it? As you create a probability matrix, we have to go in an iterative method. Every time you try to calculate the probability, and we'll also decide on the emission probability. So we'll, for example, you have a sentence which has deal, talks, fail. Now the two tags which are identified are noun and verb. Here you have an transition where you have the start to a noun or start to a verb, a noun to a noun, noun to a verb. Now what it is, it identifies whether it is from the start. If you take now deal, is it a noun or is it a verb? If it's a noun, the percentage is probability is 0.8. and the verb, the percentage is 0.2. And then you have the emission with, if it's a noun, it is 0.2, 0.05, and zero point 0.2. Here it is 0.3 together. Now, how do I define it? This we'll talk in terms of deal. Okay, when I talk in terms of deal, if it is a noun, it is the first character, and before that, what happens is start. So I'll take zero point 0.8 as the probability. Since it's a noun, the emission probability is 0.2. So I'm multiplying it to be 0.16. And then if it is a verb, what happens if it is a verb? The transition probability is 0.2. The emission probability is 0.3. So I get 0.3, 0.06. Now, the probability of deal being a noun or a verb during the start of a sentence has been estimated. Based on the highest probability, deal is likely to be noun when it is there in the start of the sentence. So we have taken 0.16 for the next case. Okay, so 0.16 with talk. Now you have two options. It's a noun, and therefore we'll take it as noun to let the talk be a noun, or the talk can be a verb. So what we'll say, 0.16 into, if it is a noun, it is 0.4 into talk is 0.2. So 0.16 into 0.4 into 0.2. Similarly, if it's a verb, it is 0.6 into 0.3. So 0.16 into 0.6 into 0.3. Where did this 0.6 come from? 0.16. 0.16 came from the previous higher value, where it is said that from a noun, it is considered to be a noun, or it is likely to be a noun. And the second one is from noun, you have two options. If talk is identified, deal is identified as a noun, talk can be either a noun or it can be a verb. If it is a noun, I'll go, since you have considered deal to be a noun, we'll take this particular line. This 0.4 into 0.2 from here, and it is 0.6 into 0.3 from here. So you got it, you have an answer over here. Now the highest probability is 0.0288. So now what has happened? Talk is likely to be an verb, and therefore I'll take the highest probability and move on to the next step. Okay, now again you have two options. From a verb, fail can be a noun as well as a verb. If it is